Once you can put like the full path like this. Which that should work. Just to find the. And perhaps in Windows also it changes how to find the path or not.
So on the speaker, Xiao Xue will be
So that
talking
should be
about
like straightforward.
induced by frequency. The signals in EHT and ngEHT polarimetric.
The difference that here it gives. Oh no, but he also has. No, wait.
Okay, it's first of all, thanks for the introduction. It's a great honor to be here talking about this topic, searching for axion-induced birefringence signal in EHT and ngEHT polarimetric data. So this work, the contributors include Yifan Chen, Yuxin Liu, Lusen Lu, Yosuke Mitsuno, Jinshu, Qiang Yuan, and Yue Zhao. Unfortunately, none of them are able to come here, so I'm the only person who is in this on site in person. My name is Xiao Xue. I am from University of Hamburg and also at DESI. They are both at Hamburg, Germany. Okay. So first, I would like to make a brief introduction of axion and axion-like particles. So this term comes from particle physics, where axion and axion-like particles are very well-motivated hypothetical particles. It means that many theorists believe they exist, but right now they haven't found it. So axion is first proposed to solve the strong CP problem. On the other hand, the axion-like particles can be derived from fundamental theories with extra dimensions. And the axion and axion-like particles, they have a typical periodic potential that well, I have showed here, where A is the axion field, Fa is the decay constant, Ma is the mass of the axion, and as you can see, there's a cosine function here, which means that which suggests that the maximum potential that the axion can have is at approximately equals to Fa. And what's more important about axion is that it has a unique interaction. Unique interactions with standard model particles, and we usually call it the CP Valentin terms. So these interactions can be divided into interaction with bosons and the interaction with fermions. Here, the interaction with bosons, including interaction with photons and gluon. Gluon. Sorry, it's a mistake. And here the interaction with fermions include interaction with neutrons and electrons, and also can be alien fermions in the standard model. So what is suggested by the first interaction, which means the interaction with boson, interaction with photon, it suggests that there can exist a axion-induced birefringence signal. Which means that with the presence of the axion field, as the light, polarized light travels in the axion field, it can experience the change of the position angle, which is the change, which is defined as the change of the direction of the electric field. And this change of the electric field can be is proportional to the coupling constant Ga gamma, and it is also proportional to the strength of axion field. Okay, so how this is connected to the black hole is that we consider the superradiance mechanism, which means that around a black hole that has a relatively large spin and has a certain mass, and it can create a very dense axion field that has a almost maximum value, which is almost equals to Fa. The axion field created has a mass that is related to the mass of the black hole, which means that when the mass of the black hole is larger, the mass of the field is getting smaller. Okay, so here the superradiance condition asks the spin of the mass should be at least 0.5, which is actually the case of the black hole M87 star, based on the observation EHT made in 2017. Okay, so on the right side, don't know if you can see clearly, is an example that we made to show the axion birefringent signal induced by the axion cloud around the supermassive Kerr black hole M87. So here is what we do is that we add axion field in a radiative transfer equation. So the conditions we choose, the software where we use is IPO, and the accretion flow, which we use theoretical accretion flow, which is RIAF. So this model is proposed by those two papers, and the actual parameterization we use is from the second paper, which is the authors includes Avery Roderick. And also here the inclination angle is chosen to be 17 degrees. Well, we also choose vertical magnetic field and the subcapillary flow, which is also supported by the EHT observation. Here the spin we choose for this calculation or simulation is 0.99, which is, you may think it is extreme, but this result do not rely on the spin as long as the spin is larger than 0.5. So right now we can, we have the form of the signal. We can actually search for the signal in the polarimetric measurement of M87 star. And here you can see the result that is given by the EHT collaboration in 2021. Here you can see in the paper, there are small lines that is in the image of the black hole, where the length of the line represents the color of the line represents the fractional linear polarization, which means that how much polarized the light is in the data, and also the direction of the line means where is represents the polarization angle. Okay. As you can see that the data can be easily separated into two pairs. The first one is between April 5th and April 6th in 2017. And the other pair is between the 10th and the 11th. So as you can see that the difference between the 5th day and the 6th day is very small. So that also between 10th and 11th. So we adopt a method called the differential EVPA that we use the difference between the data of the 2 days to use it as the data set and use this data set to search for the axion signal. The other thing we do is that we want to make the model easier, which is to subtract the time signal and put them into the sine function so that we can temporarily get rid of the initial phase problem. We don't need to simulate data at different initial phase. And here, A phi and delta phi here is amplitude and also the difference of the initial phase in the simulated data set. And here phi is azimuth AC azimuth angle. So here as you can see, we compare the observation data, delta OBS with the delta chi theory, and we can search for the signal, and if we do not find it, we can put constraint on it. So what you see on the right-hand side is the result that we gave in 2022, which is the paper accepted by Nature Astronomy. And here you can see this green area are the excluded area based on the data and using the model that we proposed. And all the other places, the blue, the colorful blue, orange and black ones are the other constraints that is from other astronomical or experimental constraints. So as you can see that our results exceeds those current constraints by a very large margin. Which is a very significant result. Okay, so now we can go to the prospects in the ngEHT era. Here is you can see another 2 green area. The first one is the current constraint. The second one is lower one is ngEHT constraint. The difference between these 2 is that we add a shorter observing interval, which means that we can get rid of the washout effect. And also we can give it a longer observation time and more data at different radii. And also we put 3 different frequencies and 1. So if we add all those things together, we can give a much better constraint than what we currently have. Okay, so here there are some features I want to talk about. You can see there is a very large blank space on the right side from this figure and also in the figure I showed before. Here, this blank space is because of we choose a super radiant axion cloud, so that those places on the right, they are not for the M87 star to explore, but for a black hole that has a different mass and spin, for example, in the future, ngEHT might be able to observe other black holes, and if they fall onto the right mass and if they their spin is large enough, they can also contribute to the speaker. But right now we have no information of that, so here we do not give more information of other black holes. And also you can see that there is a red line, say equals to alpha EM, where alpha EM is fine structure constant, which is proportional to the electric charge square. And there's, you see, I put a gray area under it. It means that they are not the physical parameter space, which means that only when C is larger than this value, greater than this dashed red line. The constraint is the parameter space. The parameter is physical. So which means that, as you can see, the ngEHT curve actually touches the c equals to alpha. It means that ngEHT in the future is able to explore all the possible parameter space that is between these two different masses. So which is quite interesting, because in most experiments in theoretical or particle physics, we usually do not have a lower limit, but here we have a lower limit. So here you can show the significance and the importance of the axion search using the ngEHT data. So here, at last, I come to conclusions. Before that, I want to make more comments on the axion search using the ngEHT data. So here you see in the square dashed area is the standard model particles. It includes quarks, which is blue ones. The orange ones are the leptons, and the yellow ones are the gauge bosons. And here is, and the last one is the Higgs. So the particle physicists know it very well. And however, even though we know it so well, and there still exists some very significant problems, including the strong CP problem that I talked about in the first slide, and also includes the problem that the particle physics does not, the quantum field theory does not is not compatible with the general relativity. And both problems actually lead to axion and axion-like particles. Right now, if we look at a larger scope at the universe, at different galaxies, and at different, look at more ancient history of the universe, you can see that those things that we know so well only constitutes 5% of the universe. And the other 27% of dark matter and 68% of dark energy, we do not know anything about it. I mean, in the sense of its particle nature. And interestingly, they can all be explained by axion, especially for axion at lower mass. So why axion is so special is a very good thing. So if we EHT and ngEHT can find axion, it can be a very, very good thing. And if we can be the first experiment to find axion, it can be even greater. And also to do this, there are also other improvements that we can make. Expect for the experimental improvements that we can easily make, as I showed here, which means that more data and better resolution, which is not a very difficult thing to achieve in ngEHT. There are also some theoretical things that we can improve, include to a better understanding of the EVPA uncertainty. And here I mention a paper, the closure trace method that is proposed by Avery Broderick, which is supposed to be able to improve the EVPA uncertainty at a great margin. And also we need to create a correct model for the astronomical background, which is, I believe, is through the GRMHD simulation can give us much better understanding of the astronomical background. Okay, so that's it. And if you are interested in this topic, you can look at those two papers, and I show the account numbers. And thank you very much for your attention.
Thank you very much, Xiao. So we have time for one or two questions before we move on. Okay, so I think everybody's tired after a long week. Could I ask, could you go back to the previous slide? I have just one very short question, actually, please. Thank you. Yeah, so you talk about Faraday rotation, but what about Faraday conversion? Is this something which is negligible in these polarized radiative transfer calculations? Because you still have a magnetoactive plasma, right?
Yes, so the Faraday rotation is proportional to the wavelengths, the inverse of the wavelengths, the square of the wavelengths. So that, but the axion-induced birefringent signal is achromatic, which means that it does not depend on the wavelengths and or the frequency. So that if we have data at more frequencies, we can easily differentiate between these two effects. Yes.
Okay, if there aren't any more questions, then let's thank Xiao again.
Yeah. If so, then we have to connect them. Okay. At least the chair. Oh. Yes. Yes. Okay.
Sorry, everybody, for the slight delay. Our next speaker is Shahar Hadar, and he will be talking to us about the photon ring. So, over to you.
Put it on. For the online people. Can you hear me now? Okay. Hi, everybody. So I'm going to tell you about the photon ring. So the plan of the talk is mainly a lightning theoretical introduction to the Kerr black hole photon ring. And then I'll discuss a little bit what kind of observables we can use to measure the photon ring and what are the relevant requirements for ngEHT. So really, I wanted to give like a very basic introduction to the photon ring from as a general relativistic effect. So geodesic motion in the Kerr space-time is determined by 4 conserved quantities: the mass of the particle which is moving, the energy, the azimuthal angular momentum L, the angular momentum around the z-axis, the axis of the spin, and the Carter constant Q, which is the most non-trivial one of the constants. And it's really, its discovery allowed I mean, it renders the problem integrable, and you can really analytically integrate the Kerr geodesics and write down the solution in terms of special functions. And that Carter constant is not related to an isometry of the space-time. It's related to a more hidden symmetry. And in particular, it's a Killing tensor. And so the Carter constant is quadratic in the momentum, the contraction of the momentum with this Killing tensor K, roughly. Okay, that's in general about Kerr geodesics. Now for null geodesics, with m equals 0, you would have thought that they are determined by 3 parameters, but they are determined actually by 2, because also the energy scales out of the problem. So, null geodesics are determined only by these parameters lambda and q, where lambda is the energy rescaled azimuthal angular momentum, and eta is the energy rescaled Carter constant. Okay, so we have only 2 parameters determining the geodesic, because the energy scales out of the problem. Intuitively, it's just the fact that a blue photon and a red photon travel on the same null geodesic. And we can think of these. Okay, so you can't see this picture here. This picture here is a screen with 2 coordinates, eta and lambda is the x-axis on the screen. So we can think of eta and lambda as coordinates on the screen. Sometimes it's very useful to think in this way. They're not exactly the Cartesian coordinates on the screen, but they're pretty simply related to the Bardeen coordinates, who are exactly the Cartesian coordinates on the screen. And it's even these directions. So if this is the spin direction, the blue arrow here, then the x-axis is lambda roughly, and the y-axis is eta. So our screen is parameterized by these parameters, who you can call the impact parameters of the null geodesic. Exactly, this definition is the definition of an impact parameter. Okay. Good. Okay. Okay. We'll manage. We'll manage. Okay. I can exit and then go back to full screen. Right. Okay. So great. Okay. So there exists on the screen. This is the screen here. You can see this red curve here. That's what we call the critical curve. This critical curve delineates 2 areas on the screen. One outside the curve, where that's the area where we kind of get geodesics, which came initially from infinity, from past infinity, and orbited the black hole and then came to the telescope. The other area is the area inside this critical curve, where the geodesics originated on the past horizon of the black hole and then came to the telescope. You can think about this also in the inverse way. If I shoot geodesics from the telescope back towards the black hole, where would they end up? Would they end up at infinity or fall into the black hole? It's just a inverting time. So, and it's the same critical curve in both cases. And this critical curve is exactly separates the sky kind of into 2 regions, the geodesics that fall out, the geodesics that fall in. And if I shoot a geodesic exactly on the critical curve, or if I receive a geodesic exactly with that critical parameter, it means that this geodesic can orbit the black hole, mathematically at least, an infinite number of times. Okay, an arbitrary large number of times, of course. For observation, I mean, you don't get really an infinite number of times, but several times. That's enough. Good. So these are these critical geodesic, and they kind of draw on the screen a critical curve, which is kind of like, you can think of it as okay. Now you can see better. Can you lift it up a little bit? Or, oh, good. Oh, that's good enough. Oh, that's worse. It was better before actually. Oh, good. That's good. Yeah, that's good. Thank you. Okay, so can I just stay with this view and just okay, great. All right, so kind of okay, how does this look like for okay, so we saw how this critical geodesic looks on the screen. It's basically traced by this curve, which is parameterized by what we call R tilde, which is the radius in the geometry where these critical geodesics can orbit indefinitely. Okay, if we tune them exactly to these critical values of lambda and eta. So there's actually a one parameter family of such critical null orbits around the black hole, these unstable light rays that can orbit the black hole an infinite number of times. And this is what we call the photon shell. Okay, that there's a photon ring which kind of tracks very closely this critical curve. There's a photon shell, which is this family, a one parameter family in Kerr of null geodesics that can orbit the black hole an arbitrary number of times. And they're parameterized. This one parameter is the orbital radius, which we call R tilde, which runs between some minimal radius, R minus, and a maximal one, R plus. Okay, so for Schwarzschild, we all know that there's a photon sphere, okay, which is at R equals 3m, which are exactly these orbits that can, these unstable null geodesics. But in Kerr, this photon sphere kind of puffs up into original spacetime between these two radii, and it's much more rich and interesting structure. Again, all determined by the Kerr solution of general relativity. So it's really, there's a minimal amount of assumptions and parameters going into this, just the mass and spin of the black hole and Einstein's equations, but it determines a pretty rich structure there. Okay, and so this equation down here just says that you can. This is kind of a parameterization of the etas and lambdas. It's like a line, right? It's this curve, this closed curve on the screen, the critical curve, and it's parameterized by R tilde. If you can see this, I don't know if you can see. Okay, next slide. Okay, near critical light rays. So that's what we were all we were saying now is it is true in general, and then we're focusing on the critical light rays. But actually, for observation, we will never have exactly critical light rays. We can only have near critical rays that orbit the black hole a certain number of times. Okay, and these will be the ones that actually form the photon ring. So these near critical light rays are close to the photon shell in phase space. There's a precise sense in which they are close to the photon shell in the phase space of null geodesics. They're controlled by three critical parameters. So their lensing properties, the lensing properties of the Kerr black hole for these near critical geodesics are pretty simple. Okay, they're controlled by three parameters: gamma, delta, and tau. It's actually three functions because they're functions of R tilde, the critical radius. They will be different parameters for different orbital radii. Okay, this gamma is called the Lyapunov exponent, and it controls the demagnification of the subrings, basically. So it controls for the geodesic traveling in the bulk near the black hole, it controls how quickly or how slowly it recedes or approaches the critical radius R tilde. So if we look at the separation from the critical radius R tilde, then the separation after the kth plus 1th orbit over the separation after the kth orbit is e to the minus gamma, where gamma is this Lyapunov exponent. Okay, but notice that this is really a function of R tilde. So for each orbital radius r tilde, we have a different gamma. So, and mapping this to the ring, this means that at every different angle along the ring, we have a different Lyapunov exponent. We have a different demagnification. So if going back to here, this is a really really cool and counterintuitive fact that different radii here in the photon shell correspond actually to different angles around the photon ring. It's very different from when we look, for example, at the moon at night and we look at different angles. They're really different angles in space-time. But here, different angles are different radii. It's a really contrived mapping here between the two. And other two critical parameters that we have are tau and delta, which are the temporal period and azimuthal period of the critical geodesics as they orbit the black hole. So because of effects of frame dragging, for example, every half orbit that we do in the polar direction corresponds to a different amount of azimuthal angle which we traverse in the azimuthal direction. So there's a very rich structure there for a rotating black hole. It's much richer than in Schwarzschild. So to get a little bit of intuition into this, let's look at what happens for a polar observer looking at a rotating black hole. So here the spin axis is into the board, okay? And let's imagine that we see some flare or some, this is the shadow of the black hole. This is a critical curve of the curved black hole. And now we see some flare happening here or some event. Okay, so it will have higher order images that underwent 1 extra half orbit, 2 extra half orbits, 3 extra half orbits. And we will all see them around appearing at different places. Of course, when the higher order images will appear closer and closer to this critical curve and build up the photon ring, basically. But the separation between, okay, and they will appear actually exponentially closer to the critical curve, and they will be exponentially demagnified with this factor gamma, e to the minus gamma. But they also have other interesting properties. Their separation in the azimuthal direction will be exactly delta. You see, and it doesn't have to be 180 degrees for a rotating black hole. Because of frame dragging, the image can actually appear at a larger or smaller angle, depends on the spin of the black hole. And they will also have some non-trivial time separation, tau, because of just the time it takes the geodesic to traverse and do an extra half orbit. And in the limit where we have several half orbits already, these are all described by gamma, delta, and tau for this small inclination case. For large inclination case, actually the situation is more complicated and rich, even more rich. Okay, so this is the animation of the photon. Photon ring animation that maybe some of you already seen. Oops, I did something wrong. Sorry. Oh, okay. So there is an n equals 0 image, which just comes from the geodesics which are weakly lensed. This comprises the main part of the emission. And then we have n equals 1 geodesics, which undergo 1/2 orbit around the black hole before going to the telescope. So this is what we call the n equals 1/2 orbit in the polar direction. And then we have the n equals 2, which is 2 half orbits or 1 full orbit around the black hole. These are real trajectories, by the way. Okay, and they become even they appear even exponentially closer to the critical curve. You can see that it's thinner and thinner, the appearance of the subring. And all these things together comprise the total image, which is the main emission, and on top of it, a thin photon ring. Okay. Now, so why is it interesting? Why is this photon ring interesting? Well, first of all, it's universal. Okay, it's really largely independent of the details of the emission. Okay, so for every emission, you will have this effect. If it's optically thin, you will have this effect that you see higher and higher order images of it, and they will all be controlled in the same way in the limit of several half orbits. Okay, so it's a universal thing. It tells us something about the black hole. It allows us to really test our ideas of general relativity or modifications to it. Okay, and it's an interesting question to ask. How do we disentangle the emission details from the space-time geometry? Okay, so there are several proposed ways to do it. So one is really, okay, and that's kind of the first way to go, is to look at the time averaged image. Okay, the average in time, this brackets denote average in time of the image intensity as a function of screen coordinates rho and phi. These are polar coordinates on our screen. Okay, and if we could measure that with good enough, if we can measure that with good enough precision, with good enough resolution, then we can look at two different things which can give us information about the black hole and about general relativity if we measure them well enough. This is one of them is the shape of the critical curve, the shape of the photon ring, basically from the photon ring tracks quite closely and closer as n grows, this critical curve. So if we can really measure the shape of the photon ring, also suggested by Gralla, Lupsaska, and Moroni, we can really perform interesting tests of general relativity and measure the spin. Another way to test GR and to measure spin is to look at the demagnification between subrings. So this plot here from Johnson et al., if we kind of slice along one of the axes this image here, then we will see it's composed of different subrings on top of each other, and these subrings becomes narrower and narrower due to the demagnification effect that I was talking about earlier. So the demagnification exactly is by this factor e to the minus gamma, and it's a function, this gamma is a function of the angle. So in principle, we can look at different angles and look what is the gamma at every angle, and we have if we could measure this to a good enough precision, we have a very strong test on Einstein general relativity because it's a full function that we can compare to theory. Okay, so I mean, of course, this is all in theory, but it will be a very strong test. And with super resolution, as we heard and we'll hear also tomorrow, the ngEHT may be used to detect even the n equals 1 photon, with looking at the time average image. Okay, a second method to detect the photon ring is by looking at kind of harnessing the time dependence of the situation. So, how should I run this? There's also an animation here. Should I just press on it? Yeah. Okay. Cool. So we can look at the. Much work has been done on harnessing time dependence by. This is a partial list of references. It was proposed to look at hotspot and autocorrelations and more. And I want to focus on these autocorrelation method today. So this is the observable that I'm talking about here. Is the 2-point function of the fluctuations of the intensity on the screen. So I'm looking at 2 points on the screen at different time, at the time separation between t and t plus big T, and at two different angles, var phi and var phi prime. And I'm also integrating over the direction perpendicular to the ring here. Okay, so I'm thinking about this just as a ring, which has a phi coordinate and a t coordinate. Okay, and we're looking at this 2-point correlation of the fluctuations. And we did this in a paper together with Michael Johnson, Alex Lupsaska, and George Wong. And we computed analytically the result for small inclination observer. And this observable separates nicely between the universal properties, which are determined by the black hole lensing, and the emission properties. So the emission properties, basically, this is the autocorrelation plane. So one direction here is the difference in angles, and one direction here is the difference in times between points. And we see a series of peaks, which is also self-similar. And the peak shape is determined just by the emission properties, statistical properties of the emission. And the locations and relative magnitudes of the peaks are determined by the lensing. Okay, so it's a nice way to separate between universal properties and non-universal properties. Okay, and yeah, good. So about requirements, so just looking at these two different observables that I was talking about. So of course, looking at the time average image, the most important thing for us is the resolution. I mean, the challenge here is just that the photon ring is a narrow feature. It's a thin feature on the screen. And to resolve it, you know, we just need to crank up the resolution as much as we can. Or even use super resolution methods, of course. The autocorrelation observable that we talked about, that has a totally different requirements. Okay? And maybe at some situations, they would be easier to meet. For example, increasing the temporal resolution. That's relevant for Sagittarius star. Of course, for I mean, the challenge here is basically when you make a movie of the time dependence of the emission, that the temporal separation between frames should be smaller than the light crossing time of the black hole. Okay, because we want to really see the movie and we want to see the echoes, the light echoes of the different flares and different fluctuations. So we need a temporal resolution of the movie, which is smaller as possible than the characteristic light crossing time of the black hole. So for Sagittarius star, we need to go below 20 seconds, right? I mean, that's the light crossing time. And for M87, we're talking about several hours, so that's not really a problem. And I should start finishing. Yeah. Okay. Okay. So that and I also wanted to point out a recent paper which is connecting. I mean, recent paper with Dan Capets, Alex Lupsaska, and Andy Strominger that appeared a month ago in the archive, in which we kind of connect this photon ring to more fundamental issues in black hole physics, to more kind of fundamental puzzles. So I think it's a good way for us also to find motivation to measure this photon ring. It's really a fundamental property of black holes. So that's and so yeah, I will conclude. So the photon ring is universal and it stands out in images. There are several proposals of how to detect it, and it's a very very okay. So let me just stop here. No, no, I'm finished. There are several ways to detect it, and yeah, it's just okay. So I'll say just one more sentence that it's just a nice feature because it really connects both to black hole theory and both to black hole observation, and it's a well motivated thing to go for us, and I think it's really doable. Thank you.
Thank you very much, Shahar, and sorry for having to cut it. It's just we have one more talk before the
Yes.
coffee break, and it's
Yes.
not your fault. There were technical issues, so,
Okay.
so thank you. So we have time for one or two quick questions while Hector sets up his talk. So any questions? There's a question right at the back there. Sorry, thank you.
Coming.
Sorry, Teresa.
Okay.
Thanks. First, I excuse myself for sitting in the back. So. No, thank you. It was an excellent talk, extremely interesting. I would like to go back a little bit, back to basics. So if we go back to Jean-Pierre Luminet's original drawing of the black hole shadow in 78, which is done for a Schwarzschild black hole, there are two rings. You have the photon ring, and then if you go outwards, there's like a black area, and then there's the ISCO, the inmost stable circular orbit, that also kind of defines a ring. So can you explain is the ISCO like important also in connection to this, and how is
Like-
that modified by the curved black hole?
Like where it appears on the image?
Yeah, exactly.
Right. So I mean, well, actually, this is a good slide for it, right? I don't know if you can see it, but here you can see things orbiting even inside the shadow, right? I mean, and there's no contradiction or anything, because I mean, it's just so right. It's not it's not, I mean, there definitely can be light that appears. That it's not like things coming from inside the horizon or anything. I mean, there can be things orbiting the black hole and still appearing to us as if they appear inside the critical
But
curve.
shouldn't the inmost circular orbit be outside the photon ring, not inside?
Well, but it's true, but the question is, you know, because this is such a contrived lens, you really need to just calculate the geodesic and see where it appears on the screen. Even if the ISCO is at a larger radius than the photon shell radius, it can appear to be inside the critical curve, because the critical curve is kind of the curve determined by geodesics that you throw in from infinity and you see what comes to it. So it's kind of a different question to ask. Yeah, but it is very confusing. Yeah.
Okay, well, I think we're out of time, but thank you very much, Shahar.
Thank you.
Our next speaker is Hector Olivares. He'll be talking to us about accretion onto Proca star.
Does it work? Okay.
Thanks, Hector.
Okay, thank you very much for the introduction. So indeed, what I am going to talk about is accretion flows onto Proca stars. I should mention that this is not completely my work, but this is mainly the work of a master student that I am co-supervising. Also in collaboration with these collaborators. And I will also talk about some previous work on related topics, also with collaborators here present in the in the room. So, well, I think it is no news that there is a need for new fundamental physics. This comes from many directions that tell us that our current understanding of physics is incomplete. So from cosmology, we have, for instance, the problem of the dark components of the universe. We have the problem of knowing which is what was the field that caused inflation in the early universe. And we have also the conflict between quantum theory and gravity, the problem of non-renormalizability of gravity, and the black hole information paradox. So we know that there should be something more than what we know at present. The approaches to tackle these problems have been several. One of them is to look for more fundamental theories. And this is the case for string theory or for long quantum gravity, but there are also more phenomenological extensions, such as extension to general relativity, such as f of r or f of t theories, as modified Newtonian dynamics. And there is also the possibility of adding new fundamental fields. This is the case for hypothetical particles such as WIMPs, as pseudoscalars or scalars, such as the axion. Or other more complicated particles such as vector or dark massive photons. In this talk, I will explore some consequences of this particular approach. So, well, this is in particular relevant for the Event Horizon Telescope and the ngEHT, not only because it is exploring a regime of gravity that was not explored before, but also because precisely in this regime of strong gravity, some of the most important effects connected with this extension are expected to take place. So here, well, in this diagram is not very rigorous, but here I want to present you some cases of what can happen in the galactic center, when some of these extra fields start to interact with the central black hole. So one case is that the halo of dark matter is very diluted, and the black hole is very small. Then if the black hole is very small compared to the Compton wavelength of the particles, probably there will be almost no interaction between them. But in case the wavelength the particles start to be comparable with the event horizon of the black hole, then we start to have the phenomenon of supereigens, about which, that has its own ways of being tested, as it was nicely shown in the talk by Xiao Xue. This is in a different. Normally, these supereigen clouds are studied in a regime where the black hole mass is too large compared still to the mass of the cloud. But if the mass of the cloud is bigger, then it can have effects on space-time by its own. This is the case of Hale black holes as the solutions that are self-gravitating and that were studied by Carlos Herdeiro. In fact, the cloud that surrounds the black hole can have so much effect on the space that it can have its own ergo regions, as is the case for what is shown here. So here there is a black hole with its event horizon and its ergo region, and the cloud that is around it forms an ergo torus. And finally, there is a last limiting case that is at the extreme, in which the cloud of the dark matter field is so massive that the black hole is not there anymore, and the compact structure that is located at the center of a galaxy is completely replaced by a collapsed structure made of this extra field. This is one of the objects that are known as exotic stars. So, but if any of these objects exist in reality, whatever object it is, it must, if real, it must interact with a universe field of plasma. So all the possibilities of detecting effects from extra fields will be limited and affected by our understanding of the plasma. Here you have some cases of how the plasma properties affect the appearance of something as fundamental as a black hole shadow. So in this case, the optical depth of the plasma doesn't allow us to see the shadow. In this case, the physical effects associated with the ISCO or with producing an inner edge of the accretion flow produce a shadow that is larger than the shadow size that is predicted by general relativity, which is indicated by the dashed line. In this case, there is so much Doppler boosting that one of the sides of the image is very bright, and when seen at limited resolution, this will not be seen as a ring, but just as a bright spot. And finally, there is this case in which the central brightness, the precious, has a size that is comparable with the size of the black hole shadow predicted by general relativity. Well, this is also important when looking at these exotic objects that I mentioned in the previous slide. For instance, there is this work from 2016 in which images of tori that surround boson stars and black holes are produced, and it is concluded that there exists a degeneracy, and that images of boson stars could in principle be mistaken by images of black holes. In this work, the torus that is surrounding this object is put there by hand, and therefore the size of the size of the two let's say shadows, even though they are bright, they are actually central brightness depressions here, is comparable. But this is completely a consequence of the size that was pre-specified and of gravitational lensing. So, well, we were then curious to see what would happen if instead of adding a torus by hand, one would dynamically evolve the plasma and see which kind of structures form naturally around it when it is free to explore even the interior of the boson star. Which so. Before going further, I would then like to explain what are the properties that are expected for boson stars. So boson stars are produced by gravitational collapse of a scalar field, as I mentioned in the beginning. They are expected to be very compact, but also to have no event horizon. they should also have no singularity and being made of a field that interacts very little with the rest of the standard model fields, that is of practically dark matter. They also have no surface. They have a maximum mass that depends on the mass of the boson. This, by the way, is wrong. It should be a Planck mass over mass of the boson times the Planck mass, and the solutions can be found by solving simultaneously the Einstein and the Klein-Gordon equations. Here there is an example of the space-time of one of these boson stars compared with the metric functions of a partial black hole shown in dashed lines. So you can see that the metric extends to the horizon, that there is no singularity, and there is also no event horizon. So as I was mentioning, we wanted to see what happens if one does a GRMHD simulation on one of these spacems. What are the structures and the images that we obtain? So this is what we did in this paper that appeared published on 2021. Here you can see images of black holes in the top row. So this is a partial black hole, a Kerr black hole, and these are images for a boson star. Now, something that is very surprising and unexpected to see is that, contrary to our expectations, that when the matter was free to explore all the potential, well, it would concentrate in the center. Instead of that, it forms as an image that is very similar qualitatively in structure to that of a black hole. We see something like a central brightness separation that looks similar to a shadow, and we see a bright ring. However, interestingly, when we look for the origin of this feature, it is not a real shadow. It cannot be, because the boson star has no cross section, or no capture cross section, because it has no event horizon. So what we see here is nothing more than an effect of lensing of an evacuated region that appears in the center of the simulation. Here, these are GRMHD, well, snapshots of a GRMHD simulation. Here is the Kerr black hole, and boson star here, and boson star. So as you can see, the maximum of the density is concentrated away from the origin. This produces an evacuated region, and later lensing effects produce this type of image. So just to make an advertisement of the code on which we did the simulations, which is a code that I contributed to developing. So this is the black hole accretion code. In case you want to try it, it's publicly available in this website. And this code was built having in mind the possibility of making these simulations on alternative spacetimes. So adding new metrics is relatively easy. The structure is very modular, and there is only a single place where one has to enter the metric components. The derivatives are calculated automatically using numerical methods. And there is even a tutorial on how to add custom spacetimes. I have to say that this is not publicly online, but I can give it to anyone that is interested upon request. So, well, going back to the origin of this evacuated structure. So we see indeed that there is a magnetohydrodynamical explanation on why this happens, why we have this evacuated region in the middle. So this is related to the mechanism for angular momentum transport in GRMHD simulations. So in accretion disk, the main mechanism that transports angular momentum is thought to be the magnetorotational instability. And in order for the magnetorotational instability to be active, it is necessary to have a specific rotation profile in the accretion flow. And the requirements are not very complicated. It just needs to decrease with radius. So what happens here for the case of this particular boson star, the mass distribution of the scalar field produces circular geodesics that are not always decreasing in rotation velocity with radius. So there is a maximum of the rotation velocity, and we see that indeed the inner edge of the torus coincides with this maximum of the rotation velocity profile. This is very interesting because it allows to predict to some extent what would be the size of the dark region based purely on the space and properties. We use this to explore the parameter space of boson stars and see if there were possibly candidates that to be black hole mimickers by having a dark region of a similar size of a black hole shadow. So by exploring the parameter space, we concluded that this is not possible for this kind of boson stars, that the size was larger than 0 only for unstable boson stars. And well, to confirm this, we have repeated the GRMRT simulation, but with a boson star on the stable branch of the family, and for which no dark region is predicted. So not surprisingly, but nicely, we found that for this case, indeed, there is no central brightness depression. It looks like a bright dot. However, well, these are not the only objects with these properties of having no surface and no event horizon. So there are more families of these objects. And one of the simplest that can be constructed besides boson stars are what are known as Proca stars. Proca stars are exactly the same, except that instead of being made of a scalar boson, they are made of a vector boson, a massive vector boson. These are very interesting because they have, in contrast to boson stars that are thought to be unstable when rotating, there are cases of, or actually most of the cases of Proca stars that are rotating are also stable. In addition to that, we saw that for boson stars, the space of solution had only non-zero central brightness depressions for members in the unstable family. In this case, for Proca stars, there are members of the stable branch for which the maximum of the rotation velocity profile is can have sizes that are comparable to black hole shadows. So with this master student, we tried to make simulations on these spacetime to see if the prediction was fulfilled. And interestingly, well, when doing these 2D simulations, we saw that the prediction was fulfilled with much accuracy. So here, the expected inner edge of the torus should be located at around 6M, and well, it is in general in general a good agreement. So this is density, magnetization, and this is a proxy for the synchrotron luminosity. So so around here we also have an evacuated region. However, well, the analogy is not perfect. We have, in general, because these objects are much less relativistic than black holes or than the other boson stars, we will have not as strong lensing as we have for black holes. So this is, for example, how you see a black hole at high inclination, but for this case, one would see almost no lensing, and therefore would not be black hole mimickers at high inclinations. Also, being not so relativistic, there is not as a strong Doppler boosting, and that would be also a way of distinguishing. And finally, the sharpness of the ring would be much different. Also, well, since the geometric properties of the image would depend very much on the plasma properties rather than on spacing properties, multi-frequency observations should easily distinguish between the two objects. So, well, this is so far about 2D simulations. However, well, one knows that the turbulent properties are not well captured by 2D simulations. One needs to go 3D. And this is what we did next. I will show you a movie that is not in the that is not here in the presentations because it could not be displayed on the Mac. But I don't know Can you please? Sure. So this is a movie on the thank you, on the equatorial plane. So we hit play. It starts accreting. There is, unfortunately, the time is not shown. So it seems that the central evacuated region is forming, but actually, in the end, we have everything filled of plasma. So, well, this is very interesting because it is very much in contrast to what we saw for the case of the boson star, in which the central evacuated region was formed even after the center was filled of plasma. So this is the current state of the project, and well, the question is what happened? What has happened in this case? What changes in 3D with respect to 2D? So evidently there is some mechanism of angular momentum transport that is probably not the MRI, because well, according to the rotation velocity profile, it should be suppressed. But there can be still other mechanisms that produce this transport. One can be spiral shocks, or a non-axisymmetric instability as the Papalouis Pringle one. So one possible difference between the case of the boson star and this Proca star is that since the boson star was much more relativistic, the radial velocity close to the inner edge of the torus was much faster, and it is possible that there was some causal disconnection that didn't allow some modes to propagate backwards and destabilize the torus. So we are still looking for what is the exact difference that happens. But well, the lessons that we learn from this is that in the end, predicting the presence and the size of a central magnetic suppression in alternative spacetime probably requires an even better understanding of the magnetohydrodynamic effects, and that GRMSD simulations are still essential to explore the properties of accretion on alternative spacetimes. Finally, there is one last thing that I would like to comment, and is that all that we studied so far are an extreme case, a case in which the extra field occupies well all the mass, and the central black hole practically doesn't exist. But some more realistic scenario would be something in between, as the heavy black holes that I was mentioning. So in practice, for the ngEHT, what would be interesting to look at will be for signatures of these fields surrounding the black hole and not completely replacing it. For this, it would be very interesting to have a larger dynamic range that would permit to look for effects of the plasma a little away from the black hole. For instance, looking if there is a rotation that comes from space-time due to the cloud that surrounds the black hole. But well, the conclusion is in the end is that we need to perform more GRMSD simulations and to keep exploring the properties of these alternative spacings. And thank you very much.
Thank you very much, Hector. So we're already in the coffee break, so I see a hand raised there, so please, Shahar.
So regarding the M87 image that we have today, I mean, does that already constrain some of these models? The fact that we do see a pretty significant brightness depression and we see a Doppler shift, for example, does that already rule out some of the models for M87?
Yes, well, regarding the boson stars that I showed, so the parameter space for that kind of boson star that was a minimally coupled phi square type of potential boson star, I would say that those are completely ruled out for the mass measurement and for that size of the ring that was observed. I would say the same for the case of Sagittarius A star. So I would say that both of them rule out the possibility of being minimally coupled pi squared potential type boson stars. But I would say that the resolution that we currently have and having those observations at single frequency doesn't allow us yet to rule out other possibilities of horizonless compact objects that can well have different spacings. So for that, I think we need to go to the ngEHT to have more resolution and to have multi-frequency observations.
Okay, I suggest we break for coffee now. As it was, there might have been another question. I saw a hand. No. Great. Okay, thanks, Daniel. Then, okay, thanks everybody. Thanks to all of our speakers in this session. Thank you again, Hector, and see you all in 20 minutes.